Hello, everyone, and thank you for joining our workshop for this year, FLUXNET Early Career Workshop. So we had it kind of special this year, having it virtual and across 3 time zones. So we're just starting the session, which is for the last time zone for today. And our topic for today will be reviewing the flux tower design and instrumentation. So we'll be hearing from 2 amazing speakers today, Dr. Stoy and Dr. Marcy Litvak. So we're gonna have a review of the technicalities of like having a flux tower. And please feel free to ask any question. We'll have a presentation 15 to 20 minutes followed by a question. And then we have also a Slack workspace that we created for that workshop, where also we can have these discussions during the week of our workshop. So please feel free to put the question in the chat or after the talk, just like say them out loud, and the moderators, Yumi and I, will make sure to ask them. And without further ado, we would like to start with Paul. I'll start with you, Paul.
Okay, let's do it.
Thank you.
So, okay, thanks, Tracy, Yomi, and Kristen. Thanks for organizing. Thanks for the invitation. Thanks everyone for being here. What I was going to talk about, and Marcy and I had a very brief discussion about this morning, because we don't really know how the overlap is going to look, is just some practical aspects of tower design, with a focus on. Let me share my screen.
Can you share your screen? Okay.
Yep. With a focus on just what I think is best to do. And what I realized looking through Slack is, everybody here, have most people joined the Slack channel? What I want to point out to people is that there's a really, really nice presentation that was posted in the Slack channel by Dr. Kang from South Korea. What this talk goes through, and I think it's great, and I think it should be shared with everybody, is just some really relevant aspects of where to go for basics, right? Different types of towers, tripods, triangular type towers, other towers, how to actually, elements of actually installing it. Like, these people are very fortunate, they can actually bring machinery into their site. Usually it's not the case. How the different types of towers look, where you want to put it, why you want to have a footprint model in place even before you start, and that you want to put it kind of not too high so that you're missing your ecosystem, and not too low that you're down the roughness sublayer. And what I'm going to focus on is that you can actually probably relax that quite a bit. The other things that were discussed, and this is all quite relevant, is kind of some practical aspects of mounting sensors. There's some really great things to do. Like, when it comes to leveler tool, like, your iPhone is probably the best leveler that we have nowadays. It's quite remarkable to just use an iPhone up there as a level. And how to put things not too far and not too close to the tower. So all of these are really critical, right? Critical aspects of understanding the flux system. Things we may or may not have a lot of control over, like what the instrumentation is, its spectral responses, right? Aspects of sensor self-heating that all become important, and different corrections. Now, with that, okay, we know that there's eddy covariant systems. We know that we might be installing one. We know that we might not have a lot of control over how it looks or where it goes or what it's doing. And so what I wanted to focus on is sort of some general ideas about how to best get the best data from eddy covariance towers. And sorry, there's a fly flying around me. So something I often like to say, right, when it comes to understanding the data, is don't trust the data, okay? Make sure, oh, there's the Slack channel link, right? Make sure that when things are coming at you, that you look at the data. And what do I mean by look at the data? That means simply make a plot, even in the field, see how things are going, and use that time series and use that knowledge as a guide to keep your data as consistent as possible. So environmental data are guilty until proven innocent. And for this talk, like we just talked about, that presentation by Dr. Kang is great. So when you're trying to build a beautiful tower, right, you'd like it to look something like this. Okay, we have an eddy covariance system here that is just in the constant flux layer above the roughness sublayer of a wheat canopy that's going to be growing, but it's not going to be growing very much. We have a perfectly placed temperature humidity probe at 2 meters, right, just like you're supposed to. We have radiometers that are not getting in the way of the eddy covariance tower. That's a sonic distance sensor. We're also measuring NDVI in real time. So I know that this is set up well because it was set up by a fantastic technician I was fortunate to work with. His name was James Irvin. He still sets up towers in Montana. And it just, everything is, there's a nice soil system in here, right? All the wires are nice and controlled, and we're going to get some really good fluxes from such a tower. But the reality is it's not always the case, right? And so we want to ask, when we do build our tower, okay, are we going to, at the end of the day, be happy with what we did? Or we're going to say, oh, I wish that I did this differently, or I bet that that's going to be a problem eventually with the data. The more we know about the tower and the system and its design, the more we're going to be able to make improvements post hoc. We're going to be able to make spontaneous improvements in the field. We're going to ensure that the data that we have coming in are the best that they can possibly be given the circumstances. And sometimes the circumstances aren't entirely great, right? We like to always think that we're measuring these perfectly homogeneous ecosystems and that all the soils and the leaves are doing what we would like them to. But that's not always the case. So this is a cornfield. This happens to be an extremely sandy soil, as you can tell. It's a really kind of a cool site in central Wisconsin. That was really asking a directed research question about, do we need to irrigate these lands to make them productive? And the answer is this year we got lucky, we didn't, but oftentimes you would. So if we have, right, something that is more heterogeneous than you think, right, before you even get your instrumentation started, you want to have a framework where you can overlay a flux footprint on the elements of the ecosystem that you think are important. There's different types of flux footprints, right? There's different methodologies for doing so. I highly recommend the one by Natasha Kloon, which has both an R and I think a Python and a MATLAB implementation. You can simply download it online. But the faster that you have a workflow to ingest the eddy covariance data and to track it and to check it and to help it answer the questions that you want, the better your system is going to do for you. Right. So along those lines, right, when it comes to looking at the data, right, radiometers, we should probably point them toward the south or the north in the southern hemisphere where the sun mostly is. And there's still going to be some aspects of reflectance, right, because the towers are mostly going to be metal. Here we have put green tape over our kind of reflective logger box to help with that reflection. But sometimes you're going to look at the data, look carefully at the data, and notice at the same time every day, like the outgoing shortwave radiation is much, much higher than you think it should be, right? That could not be due to the surface albedo, but due to the albedo and the reflectivity of the tower, right? So you want to always have a critique of your own data, a constructive and healthy critique, and say every day at about 12:30 or so, there is just too much outgoing radiation glinting off the tower that I feel like it's best to just flag those data or filter them, right? Never assume that the data are any good. Always assume, right, that anything could happen, because it oftentimes does. One thing that happened in this particular site is that I just decided to go ahead and just do some wiring. And I thought, well, if we have some solar panels and I connect them in series, I can bring 120 volts to my system. I was thinking we'll have some voltage drop. Maybe I was used to a bigger charge controller, but I put 120 volts into a charge controller rated at 60 volts. And then about a month later, I smelled plastic and the batteries were dead, right? Because I did something wrong. So always make sure you know your instrumentation, that you know the compromises that you're making, that you know how the system works, and that you know the polarity of your what's positive, what's negative, because we're mostly working with DC power. And that you're just careful. And the nice thing nowadays is you can have all the manuals on your smartphone or your field computer. You can always just give, a quick double check and say, oh, why is this not working? Most of my morning this morning was dealing with actually a charge controller in northern Wisconsin that's not charging the batteries the way that we thought they should. We still don't really know why, because everything looks fine. So, just always always try your best to make it all work out, understanding that it won't always work out. When it comes to looking at the data, it's pretty common, especially remember from Dr. Kim's talk, he had some really big bulky towers like those walk-up towers, where if you look at the turbulence statistics for what's coming kind of from behind the anemometer, which is usually air that is flowing through the tower, that might have some turbulence data that would include the W bar, like the angle of attack, right? That is doing something different from the air parcels that are not traveling through the tower to your system. So you may need to apply something like a directional filter on your fluxes and say, man, okay, if it's coming from these angles, we're going to go ahead and say that those eddies were manipulated by the tower as much as they were by the ecosystem. We can't calculate trustworthy flux data from them. That should also be apparent, hopefully, in the, if you're using like the Mauder and Foken or other types of quality control, like the stationarity tests, right? Ideally, those will help find and flag those data. But like I'm saying, right, environmental data is guilty until proven innocent. So carefully always look at all your data. What this figure happens to be showing is like a 50 and 90% footprint in the white and the green, with some litter baskets in gray, and then leaf area index for a SAP flux eddy covariance intercomparison by a paper by Chris Oishi a long time ago. But you see the reason that we don't have anything in the flux footprint kind of coming from the north and slightly east direction is that was the air that was coming straight from the tower, which we immediately just kicked out of our eddy covariance processing routine, saying that it's not that great. Other things that we can do here, right, is if we are applying a footprint model right away and we're measuring something like a heterogeneous ecosystem, where we might not always be measuring what we intend to, right, there's every reason to believe that we can use that flux footprint as an additional criterion to rejecting data that we just don't think are that good. So this is just like a day full of data here. Way back in 2005, this is in the Duke Forest ecosystems. We have a elevated CO2 face site here, right? So every time the wind is kind of coming from the east, we're going to want to remove those data because they're actually capturing some of the elevated CO2 from our face system. And then this is that forest I showed you before. It's a hardwood forest, oaks and hickories down in the southeastern United States. And then this is private land, right? And the private landowners made a big old clear cut right where we occasionally were measuring a footprint. And this is a grass field, and then every once in a while, especially at night when it's not so windy and those data might be rejected from a U-star filter, I'm going to go ahead and say, well, sometimes it might just not be measuring what we think is measuring. Okay, so have a system and a routine set up to remove data that you think are bad. And it's okay to be a little conservative about that, right? Take away more data than maybe you think, because if we're measuring every half an hour, that's still going to be lots and lots and lots of data. So the other thing I want to encourage people to do is, just take advantage of opportunities that you can find, right? I kind of inherited a master's student one time. They needed a project. I said, well, I was living in Montana at Montana State at the time. There's a very rich person named Ted Turner, who's the largest landowner in the entire United States, a private landowner. And he loves bison, and he had bison, and it wasn't that far from campus. And he always says, you can do research on my lands if you want to, as long as you don't wreck things. So I borrowed, some eddy covariance gas analyzers, methane gas analyzer, the 77 right here, 7700. We apparently didn't have really good solar panel mounts, so we just stuck 5 solar panels. It appears like vertically. We have a little bit of a electric fence to keep the bison away, just a little bit of electricity. It'll keep the wildlife away from your system. We, did our flux processing routines, and we measured our bison, okay? And we sort of took this data from like phenocams, measured where the bison were, measured the methane flux that was coming from them, and had a nice little kind of opportunistic study of something that most people wouldn't measure. Because nowadays, when so many people are using eddy covariance, and you think, oh, the world is saturated with eddy covariance systems, this fly is killing me. What are we going to do? Everyone's measuring everything. No, there's always more things to measure, right? There's a lot about the Earth system that we still don't know. And in this era of eddy covariance, I'd like to think that we can have a lot of fun and get really creative, because we have neon ink measuring normal ecosystems. We have Ameriflux measuring so many ecosystems, right? Every once in a while, I think it's useful to just try to answer some scientific questions and say, this hasn't been done before, and I'd be curious to know if bison have more methane flux than cattle, or what happens to methane flux after lakes melt. So this is what this system is doing. We borrowed a 7700 methane gas analyzer from Ameriflux, and we put some eddy covariance systems on buoys on the ice on small lakes in northern Wisconsin before they thawed. Found some really interesting things. Like there was kind of a 2.5-week period of elevated methane efflux just after the ice melted, which I thought it would have been much faster. So you kind of learn things from this and learn about processes. And when it comes to a lot of these studies, you say, oh, we only had this much real estate on the tower to put 4 panels. That's a system that's going to be about 3 amps. Everything that's included in that picture between the closed path gas analyzer and the methane sensor. We killed our battery banks over and over. We were switching it off using a solid state relay, so not even measuring at night, which is a bummer. Had to install an entire other buoy of solar panels just to keep this thing running. So even though it's cool and fun and creative to be opportunistic, we always have to keep the limitations of the power system in mind. And when I talked about before about looking at the data, okay, look at your data often, make simple plots. Those plots don't have to be good. This is base R, a JPEG. This is a horrible, unpublishable plot. And we did it in the field, and it explains exactly why, right, our batteries died, because for some reason the charge controller wasn't charging them anymore. So we have this, the more you look at the data, the more you can quickly find out what's wrong. And to me, that's one of the most important things that you could possibly do when, using eddy covariance, is just make sure you get as much data as possible. So we have to get creative, right? There's tons of opportunities to use flux systems to ask novel questions. A lot of people say, oh, you can't measure eddy covariance here, you can't measure eddy covariance there. It's like, no, you probably absolutely can. You just have to be aware of the limitations. So this is a sub-canopy system used mostly to measure, snow melt. We used it for a bunch of different studies, right? It's underneath the canopy. It does not meet a lot of their criterion of what a lot of people would say you need for eddy covariance. And a lot of us, including some very senior people in the eddy covariance community, would say, who cares? Let's just go ahead and learn from what we can and acknowledge that I might have to filter out 90% of the data, but those that I have are data that nobody else has. When we're measuring things like, applied like agricultural systems that have combines, we'll always have this problem where you can't really, this is wheat, harvest the wheat right underneath the tower in the same way as you would other things. So here, the farmer thought it was a fun and unique challenge to try to go just around the tower, watching this enormous combine with its big choppers just skirt by right where the tower is. So, trying our best to study how systems actually work, and sometimes that takes a little bit of thinking on your feet. And most importantly, right, there's all sorts of opportunities to do fun environmental science from this. So this is a picture of an undergraduate researcher, James Minot, who's now a graduate student at Utah, in the Milwaukee Journal Sentinel, right in the front cover of, I think, the Sunday edition one time, going out and checking out one of our buoy systems that was measuring. This one wasn't measuring methane, just, water flux, carbon dioxide flux, heat flux from a lake, and just gorgeous, summer day in Wisconsin, and everything was perfect. So the more we sort of have fun with what we do and continue to build our community and do cool things, I think, the more we're going to attract more interest in our science, and the world's going to have a good time. So that's kind of what I wanted to talk about today mostly. And I was going to now turn it over to Marcy to talk probably about some, much more applied aspects of how to really build tower systems and sites.
That was awesome, Paul. Yeah, no, actually, because I also saw Dr. Kim's slides, I kind of stayed away from the nuts and bolts because I think that was covered so well in that talk that I started to think about what other gaps could I fill in that weren't covered in that talk. And what Paul covered is perfect because I think they'll go together really nicely. Okay, so let's see if I can actually change this. Okay, so I have a gradient of towers in New Mexico that we call the New Mexico elevation gradient. We have 9 towers. They're spread kind of throughout dominant ecosystems across New Mexico. You guys know this, right? You know what towers do. Let's see, actually, some of these are on animation. They're perfect for giving us kind of a small footprint view, snapshot of the ecosystem and the drivers that are driving them. So what I wanted to kind of talk about, and hopefully this will generate some discussion, are kind of thinking beyond the nuts and bolts of just setting it up, and think about you know, kind of the philosophy behind the tower in general, in terms of, is it the best tool to use for your question, and what is your question? Because, you know, I know when I got my job here in New Mexico, there actually were, I was fortunate, let me go back here for a second. I was fortunate in that these 2 towers, high elevation towers in New Mexico, were set up as part of NSF funded project. It was a science and technology center called SARA. Nobody was running them. These 2 low elevation sites, the creosote bush and desert grassland towers, were set up as part of a NASA funded project to validate remote sensing products. So I kind of inherited these. I walked right into them. And then I had money in my startup to set up a new tower, and I was able to write a new grant. So I thought a long time about what the best place is to put what other towers would I need. And so what I came up with is adding these middle elevation sites so that I would have the elevation gradient and I could ask questions about that. So along those lines, I think the questions that you all should be asking yourselves as you launch your research programs, you know, are basically determining where to put these towers. Is think about the question and think about the hypotheses, right? How do you come up with them? Are they compelling? Are they novel? Are they fundable? Because that's super important. You need to be able to write a convincing proposal to get your research funded. How do you know? Like, how do you even start that process? I mean, I'm sure you guys have all these conversations and have had them with your advisors. I think reading the literature, looking at agencies, federal agencies, they usually put out, you know, reports that talk about their vision for the future, their strategic plans. I would definitely look at those. Taking advantage of opportunities, like Paul just mentioned, is super, super important for thinking about these as well. You know, in terms of writing a convincing proposal, one of the things that I always tell my students to think about is coming up with a really good conceptual framework to show where are the gaps in our understanding and how can I fill them, you know, rather than there is, I think, there's something to be said for if you start in your new job and there's, you know, a biome right across the street and nobody's been making measurements in there. If you have methodological issues you want to work out, I think it's great to set it up there, but I would caution you against using your resources just for that if you don't have a compelling question, if that makes sense, right? I think the other thing to really think about is a flux tower the best tool to use to answer your question? I'm a big fan of flux towers, so I'm not trying to discourage you. It's what I built my whole research program on. But I think there are things to think about. You can definitely be creative, and I think you can put them in areas that you might not have thought of, but there are a bunch of things to consider, right? The footprint, like Paul mentioned, topography. You know, there's been a group out of the Northwest that has been thinking about, you know, ways to put a flux tower on a slope, and can you actually adequately measure fluxes in that way? Ease of access, this is a huge one, right? I've worked on towers that in my as a postdoc, the first tower that we set up was, I was a postdoc with Mike Golden at UC Irvine. We set it up in a marsh right next to campus. We could walk 10 minutes to that, and we could work out all of the details that Paul was saying right there, which was amazing. When you set up a tower that's 4 hours away, that's harder to do, right? Power, do you have sufficient power? Paul gave a really good example of that. Spatial heterogeneity of vegetation, of land cover. Again, Paul covered that. Super important to think about. Longevity, how long do you need this tower to function? Are you asking a short-term question? So you just basically need to be able to set it up on a temporary basis? Or do you want, is your goal to set this up and let it run for many, many years? There's kind of different criteria that you would use for that, right? Something we've unfortunately had to deal with here in New Mexico, susceptibility to vandalism. When I started, we had one of our professors who wanted to make measurements. We have a bosque, we have the Rio Grande runs through New Mexico, and we have a forest that is, about a kilometer, roughly 500 meters to a kilometer on either side. And he really wanted to understand the role that the bosque was playing in terms of driving evapotranspiration and what role different species were playing in altering that. And it's, there's access, open access to that. One of his towers was pulled down. One of his towers was used for target practice. So you need to think about that when you want to set up a tower, right? And then susceptibility to disturbance, which I have a lot of experience with, and I'll talk a little bit more about that in a minute. The other thing, and this is kind of like, been one of the things that's been driving my research program, is one tower enough to answer your question? In some cases, the answer is yes, but paired towers, clusters of towers can be a really, really powerful approach. And that's something to consider. Let's see. Other things, what other measurements or techniques do you need to add to what your tower measurements to be able to answer your question or test your hypothesis? So everything really needs to come back to your question or your hypotheses that you set out at the beginning. And then who do you need on your team? And this again comes back to your questions and your hypotheses. It also, I would encourage you to think strategically in terms of funding. We just hired a new professor last year, and she just got funding from DOE EPSCoR. She put together a team. They were all early career researchers, and they all are from EPSCoR states. So really think strategically about the best people to put on your team that will enable you to get funding. And there's a bunch of, just think about it from every different angle, because that's super, super important. These things on the left, they're covered really well in the slide deck. Paul talked about a lot of them, right? So these are kind of parameters that are typical to consider. And, I'm sure Paul and I can talk more, and it seems like you'll hear more from that lecture later on today about all of these. They're really important parameters to consider. But the other thing I want to mention is there's a bunch of things that, like, as I've been running these towers for, I don't know how many years, probably more than I want to think about it. Just a lot of the things that I have encountered through my career with respect to towers that I did not think about when I first set them up. One is vandalism, right? Like, I never would have thought that somebody would have put a chain around a tower and drove a truck to drive it down just for fun. So that's something you need to consider when you're setting up your tower. Theft. We had in one of our sites, somebody drove up in a quad, I can't remember what they're called now, and stole all of our batteries. So because of that, we installed gates and locked all of our boxes. Cows, those fences that Paul showed to that are just solar charged fences are the perfect way to keep out cows. They can do a lot of damage. Rodents. We have had rodents even just recently that have gotten into our boxes, and they chew up all of our wires. Birds, I'm sure you guys are all familiar with they like to poop all over your equipment. Radiometers, your open path ergas. We've had lots of interference from birds. Bears, fire, some of these you can prepare for, some of these you can't. Tree fall. We've had a tower fall on our guy wire at one of our high elevation sites that we had to take care of right away. But we also just in the last 3 weeks, we had a tree fall over one of our repeaters that we're using for our wireless data transfer. And lightning, right? So you can do as much as you can possibly to protect your systems from lightning. But, if your system receives a direct strike, there's not a whole lot you can do. What we've had more issues with are nearby strikes that have, wasn't necessarily obvious right away, where we had a bank of our sensors just go out. And once we started looking at lightning strikes in the area, we were able to put it together. but those can dramatically alter, especially things like soil water content sensors, that if you're not paying attention to dramatic changes, can really mess you up. So how do you deal with all of this? My solution now is to overbuild everything. And my husband makes fun of me like you would not believe about it. But if you overbuild everything and you try to protect your equipment as much as possible, you put more time in at the front end and it can save you a lot. You know, there's ways to set up your systems where you're just getting them out there, right? And I think every time that we've tried to do that and minimize the time required, we have paid the price. So my suggestion is to overbuild and try to think of all of these contingencies as much as you possibly can. Site selection. So there are a bunch of tools available to help you with that. I really encourage everybody to do those. I mean, but things that I've noticed when I've been selecting sites, which is honestly like the most anxiety inducing thing that I have to do. I hate selecting the sites to put up new towers, but you know, there are things that that we have found, like some of the things that have creeped up that played a bigger role than I would have imagined are things like soil heterogeneity. I set up 2 towers right across the road from each other on the Sevietta long-term ecological refuge site or ecological research site. They looked almost identical above ground. When we started looking into it a little bit more, the soils in one site had significantly more clay content, which was not, there weren't any geomorphic features, you know, that would lead us to believe that that would be the case. And the increased clay content allowed higher water content, and that influenced the fluxes, right? So things like that, you really need to take the time and make the measurements ahead of time so you know what you're dealing with. The other thing, so we're moving one of our towers at the Sevietta, and we did a bunch of surveys to try to put it in a new location and understand the vegetation in that new site. We did all of these, and this, as I think about it, I think, of course, it's very obvious now. We were doing, mainly what we wanted to do was increase the ratio of blue grama grass to black grama, because we were moving from one that was dominated by black grama. So we spent a lot of time making surveys, figuring out that ratio. We did all of this in the winter and the early spring. And when we went to go set up the tower this summer, we realized that the location that we picked, it just wasn't growing very much, which we had no way of knowing that in the winter, right? So think about phenology. Think about the time of year when you're actually trying to understand your vegetation. The other thing that we have dealt with recently is rate of plant growth. So in those sites that I was showing you that I inherited, my high elevation sites, the towers were installed and the trees outgrew the tower. So we had to install a new tower. So thinking about at the beginning, what's the potential rate of plant growth and what height tower do you need? It's always easy to move your instruments up, and believe me, it's a lot easier to do that than to install a new 130-foot tower. So those are things I would definitely think about. The other thing that we have come across in the last few years that has caused us a tremendous amount of headache is cross-calibrating our sensors, and these are specifically our open path ergas from Litvak. We have 9 sites, so we probably have 13 or 14 of these open path sensors. We calibrate them every 6 months. What we weren't doing is calibrating them relative to one another. And although Litvak won't necessarily come out and say this, although I think we'll be hearing more about it in the future. Russ Scott noticed this a while ago, is that especially in the older sensors, it might not be as big of a deal with the new ones, but when you're as old as I am and you have sensors from over 20 years ago, this is an issue. There were these hardware shifts that influence the raw flux that we were measuring. And when we didn't account for those, we had very odd time series just within one site and also comparisons between sites. So we did a huge cross calibration of all of our open path ergas to each other. It took about a year. And once we applied those corrections, everything made sense. So I think that's really important to think about if you're working with other groups and trying to answer a question together, or working within your own group and you have multiple sites. So that's probably a lot of kind of random things to throw at you, but those are the things that I wanted to bring up.
Yeah, thank you so much, Professor Marcy and Professor Paul for your presentation. So now we have a time for questions. So please feel free to drop your question in the chat, or just you can raise your hand. And, yeah, I mean, you can say your question out loud. And also after the session, you can also ask questions you have on the Slack. So we've dropped the Slack link and to join the Slack in the chat. So
yeah, I think there is one question from Eileen, Q&A place. Thanks for the talk. Is it possible to get flux footprint from specific enclosed patches of vegetation, and how reliable can that be?
I could try to answer that. So the flux footprint is the best mathematical representation of where the flux came from. And the best way to do that is to use an extremely time-consuming and very difficult to parameterize, probably Lagrangian back trajectory model to figure out where every little parcel of air came to your system. That's not usually the approach that people take. People usually use some extremely effective and elegant semi-empirical methods like Catulle and Hussey. I have a very simple one that works pretty well, and I really want to emphasize Natasha Klune's work in this regard, and I'm going to find her website right here because and put it in the it's different than it used to be, because what she has in her footprint model is just very easily executable code right on the web. And I like that approach quite a bit because every footprint model that you use will give you, of course, a slightly different answer for where exactly things came from. You know, by definition, because it's different math. The better you measure the angles, especially if you're sonic anemometer, that's going to really help you figure out where things go. Oh, here you go. Thanks, Paul Ingebrand. Footprint.clune.net. What she has here, and it's just really nice, is just some nice downloads. Hit the downloads page and then start, you know, playing around with the code that she has. So the only other thing that you may or may not need to do, depending on what footprint model you use, is, you know, you're going to need some sort of map or three-dimensional, like just good representation of your site, and then a way to kind of translate that into where the flux footprint model thinks your flux is coming from. So when I was showing that little video clip, that was a footprint model, you know, 3 different eddy covariance sites as they were traversing actually a JPEG. Because JPEGs they make really horrible graphics, and they're really great for this type of research because they're just red, green, blue layers. They're an X by Y by 3 red, green, blue image, and you can just do a lot with that, quite frankly, when it comes to, you know, pretty simple analyses of fluxes. So yeah, that's how I approach footprint models, as not a person who develops them, of course, rather someone who just needs to use them like we all should use them. So I like Natasha's work the best.
We have another question from Fernando. Why should the radiometer point south?
That's a good question, right? So in the northern hemisphere, it should point south because if it's pointing north, there's a really good chance that the sun will be directly blocked by the tower if it's not put at the exact top of the tower. It can be, especially for tall towers, exceedingly difficult to put something at the very top of the tower, because just like a ladder, it might not supposed to be exactly all the way up there. Right, it could be quite dangerous to be at the absolute highest level. So the more the radiometer is pointing south, the fewer the tower itself has opportunities to directly impinge upon the incident radiation.
think the other thing that we do at our sites whenever we can, and a lot of people do, is put your radiometer on a separate tower if you can. So if that's easy when you're working in a grassland, right? But just to move it out. So because, you know, as soon as you start putting up instruments, you've probably noticed you stomp on the surface right underneath the tower and it drastically changes it, right? So not only do you have boxes, but then you have more dirt normally than you would have available. So if you can put up a separate pole or a separate tower to make those measurements, then you can avoid the disturbance angle.
Hello, Marcy. I have a question about you just mentioned the pairs of towers, right? So I'm just curious. So that the pairs of towers can be vertical or can be horizontal to just measure the flux. And I'm just curious about whether it's vertical sensors or it's just horizontal sensors for the flux measurement. Could you provide some cases and examples about this? Yes. So I have.
Yeah, I'm happy to talk about it. I'm sure Paul is too. When I was talking about paired towers, I'm talking about arranging them across spatial heterogeneity, so horizontal. But you know, I think you could also think about paired systems above and below canopy, right? That would fit into that as well. And that allows you just to enhance, I think, the questions that you can ask and your understanding of the system. So I would say both. The questions, the way I've used them in the past is to understand how fluxes vary across disturbance gradients, how ecosystem function varies across ecological gradients. So for example, recovery after a large fire, or the influence of mortality of dominant species. So things along, or even, things along those lines are how I've used the paired towers in the past. Paul, is there something you want to add to that?
No, yeah, I think that's a good point, is that people don't think enough about vertical paired eddy covariance systems. I think a lot of times and there are a number of towers that have multiple different eddy covariance measurement heights, and it can teach you a lot about different footprints. And the above below canopy science there's opportunities to really do a lot more with that. A number of groups in Switzerland are doing some cool work with that. There's some early work by Laurent Masson in the Blodgett Forest. I think that was, alongside Mike Golden's work in California. And so, yeah, there's a ton of opportunities to use the vertical paired approach a lot more than people do. And then I think more often than not, like Marcy's saying, people put towers adjacent to each other. There's not really a definition of adjacency. And we actually tried to propose one in a paper, and then it got rejected. So it depends on the question that you have, is sort of how close is close enough to be paired. And yeah, it's kind of a scientific question that you want to answer. And can you do it? Will the landowner let you put a tower there? Or, is it feasible? Or is there going to be an issue with the footprint or the topography or something like that? So yeah, there's I'd like to think that we could do a lot more, especially now that there's like neon and the Ameriflux and just consistent data, to put a tower nearby another tower and just use that base tower as the opportunity to expand around and ask questions.
Thank you. Thank you for your answer.
I saw, yeah, and Marcy answered Mohammed's question online. Yeah, the footprint will vary dramatically based on the sensible heat flux, which is going to create turbulence, as well as the friction velocity, right, the U star, which is going to create turbulence, and in different ways, and the balance between those two things will determine sort of how large the footprint is and extent. And Marguerite has a question.
Hi, thanks, Marcy and Paul, for the presentations. I have two questions. I'm curious if you could speak a little bit more about some of the things you think about when you make your site selections for the towers. Like obviously topography and what you want to measure and what are your questions, but like if you types of preliminary data that you try to get your hands on to try and make decisions and things like that. And then I also am curious about how you do your calibrations and whether you do them in the field or whether you tend to take your instruments back to the lab and do the calibrations in the lab. I'm just curious to hear more about those two things.
You want to go first, Paul? I'll go after you.
So Marcy probably does a much better job of this than I do. So those are my kids in the background playing with the dogs. What I don't have what we call like funding, really, unlike a lot of scientists that and so when I get funding, it's usually for a pretty short-term, like growing season long or just year-long kind of tower installation somewhere, and I'm always moving my towers back and forth because of that, and because I found that I make more mistakes when trying to calibrate the LICOR instruments than the parameters of the calibration will actually vary. I tend to actually hire Ankur Desai's all-star technician, Jonathan. I don't even have my own sample gases. I don't even have a dew point generator right now. Hire him to calibrate before I install things, and then after a few months take it back. Because if I was to try, and I made this mistake in grad school, I actually messed up the calibration and lost data because of that. Because these sensors, especially when it comes to LICORs, are like not the 6062, that has to be calibrated like every day or less, but the 7500 and other things, I mean, if you calibrate them too much, the human error element is going to be more than the drift, in my opinion. So that's how I like to think about calibration, but that is very particular to my own installations. And when it comes to doing most things, I have the famous big box of wires, and I just basically like bring the box like to the site, and I just find the right size wire like until it works. And right now, because I forgot to bring a socket wrench up to a site that I've been trying to install for months, but it's been hard to get up there because of kids and other things. Like it's just, I was sounding anemometers like kind of hanging by like me like threading it in by my fingers because I forgot my socket wrench. So like so much of it is just like the more you just have a workflow to get things done is better. But I think a lot of people do things like way more by the skin of their teeth than people kind of realize when it comes to these measurements. And it's it's just normal. We just want to make things work, and we don't always have like a technician who has 20 years of experience to do anything. We have about a couple hours and hope it all works out. Marcy, do you have a much more professional answer to my?
I wouldn't say professional, but we do have, so for our towers that, for most of them have been running since 2007. And what we've settled on now is every 6 months, we will get our open path. We bring our open path back to the lab and calibrate there. And that's where the cross calibration of all of our instruments became really, really important, because we started out with keeping the same instrument at the same site, calibrating it and taking it back, but then we're losing 2 days of data. So then we started thinking, well, we can just swap them around. We'll have some calibrated ones in the lab, and that's where we really noticed this issue. I agree with Paul, like you can, it's easy to make mistakes when you're calibrating and introduce more slop into the measurement than you would care to. But doing this 6-month approach and knowing all of our correction factors that will help us cross calibrate between all of our ergas has eliminated those issues. What was your other? Oh, site selection. In terms of, obviously like remote sensing as much as you can to get an idea of the spatial heterogeneity of what you're looking at is super important, but ground validation is key. You cannot do it with just remote sensing. In this example I gave you of, well, you know, we wanted to change the ratio of blue grama to black grama. Remote sensing doesn't pick up the differences between those two species, so there was no way to do it with a remote sensing perspective, unfortunately. But the other thing that's super important is prevailing wind and knowing exactly where that's coming from. So if you don't have a nearby Met station that provides those data to you, I think that's super important to set something up so that you have some idea of where the flux is likely to be coming from the majority of the time. We're lucky here in New Mexico, at least up in my part of the world, most of the prevailing winds are from the south. And so that happens, but that changes wherever you go, obviously.
Thank you. It's funny, wind is actually specifically one of the variables I was thinking about. Like, should you set up a temporary anemometer just to get an idea of where the wind is coming from if you don't have good enough data sets, or you're not sure how well a data set represents the site you're actually thinking of? So would you do just a 2D wind? Is that enough for that?
I think so. Yeah. I mean, you just basically want to know, where is it coming from? So
Yeah.
I think that would be.
And like
Thank you.
Marcy said, you could basically assume for us that it's kind of mostly coming from the southwest, and you don't need to try to install an anemometer. Or you can get a nearby Met station. Where those wind directions are going to become important are some like preferential flows in mountain valleys and some unique flux situations.
And for sure, in our high elevation sites, that's where we had to just set something up, because it wasn't like here at Sevietta or any of our other sites. It's coming from the south for the most part, but up there things got really tricky and we just couldn't tell. So.
Mhm.
So
I mean, I guess we could elaborate on that a little bit, because it's like not like the wind's always coming from the southwest in our case, and when it's coming from a different direction, that's when it could be a really particularly interesting meteorological event that we want to measure. So, you have to, but then we've been measuring wetland forests sometimes, and we get in trouble if we like put infrastructure like where the actual wetland is, and we have to, like right now we have a super suboptimally positioned tower for the question that we want to answer, simply because wetland regulations, you're not supposed to build in the wetlands, and so we'll have to get lucky that whenever the wind comes from the northeast, which is almost never, we'll actually measure like what we're trying to measure. But you just got to do your best.
So I think no more question. I mean, if anyone still have question, please go ahead. And so just a reminder for tomorrow's session. So tomorrow will be more focusing on processing eddy covariance data and standardizing it. So we'll be hearing from 3 speakers tomorrow. We're gonna talk about like the basic principle of eddy covariance processing, with a focus on a little bit like on eddy pro. I'm gonna talk on how to prepare the data to present it to FLUXNet or AmeriFlux. And then we're gonna have also a look on the neon network of eddy covariance. So I think we're done with questions. Thank you so much for our speakers today and for all the participants. So it was, a great session. And thank you everyone for joining us, and hopefully to see you tomorrow. Thank you.
Thanks so much again, everyone.
Thank you. Tara, I just have one quick question. So
Just a second, I'm trying to figure out how to put everything to the cloud.
Sam, so how does it work about the mentoring thing?
I think we will just answer those questions on the Slack, so